Hello everyone, good afternoon. We are here for another session of domain analytics, that is wildlife. Today we will be looking into decision tree, its use cases, and we'll move on to the next algorithm, that is simple linear regression. So let me share my screen. First, we'll look into the decision tree code or how the decision tree is done, and then we'll look into a use case. So this is a data about research on captive animals. They have captivated the animals in an enclosure, and the researchers have studied about them. So what are the studies made is they have recorded the day, their feeding habitat, their grooming, their resting period, their cacking period, crawling period, and their walking period. So first, we will import the necessary libraries, that is pandas and numpy, and we will read the data. Okay. So for this data to be visualized, we have to import the data visualization libraries, that is matplotlib and seaborn. We'll see if we have any missing values in the data. Data dot is null or sum. And then we also check for the duplicated values, which we don't have any. And then the data type of the column or the features we have, which are all in an integer format, because all of these are in numerical format. Then we have, or we did, the correlation of the data. So with respect to day, feeding, grooming, resting, cacking, crawling, and walking. We now visualize the heat map using seaborn. This is a multi-variate visualization. Visualizations are of three types, that is univariate, bivariate, and multivariate. So this is a multivariate analysis of data using visualization. So here is the graph of a heat map that shows the correlation of the data. The same values, we get it here. So if we see about the feeding the day and the feeding. So you can see the data. Next, we try to visualize the data using single feature, that is univariate data with histograms. So we are visualizing or seeing the distribution of the data, how the data is distributed for each of the features, that is using histogram resting for resting. So this is the graph we get. And then for feeding, this is the distribution of the data. For grooming, and we can see a significant difference between all of these. So it's 1.01, 1.5, 2, 2.5, 3.3, 3.5, and 4. So here you can see the difference itself starts from 2, 2.5, 3, 3.5, etc. And then we have cacking, that is 0, 1, and 2 has a lot of distribution. 1 has a lot of distribution in it, and 3 and then 7 has the least. And then we have rolling. So the data here also 4.5 has the distribution of data. From this, to draw insights, we can say that the average or the animals in the enclosed area, the average of them of their trolling is 4.0 to 4.5. And then we have something, okay, one more feature in our column, that is walking. So this is next is just a listing of all the columns in the data. And then we divide the data into predictors and target. So from sklearn model selection, we import the train test split, and then we split the data. We set the data test size as 0.3, and from sklearn.tree, we import the decision tree classifier. So model DT criteria is entropy, and we are fitting the model for train, that is predictors, and also for train, that is target. And predictors, we are telling that the predictors is equal to test as target, which is nothing but the test data accuracy. So now the prediction on trained data, as we do the prediction on the trained data, we do a cross tab on train target predictors with row names as actual and column name as predictions. So, and then we get the mean of the predictions spreads for the train target. So finally is to plot the graph with sklearn.tree plot tree. So for the data, whatever you have, you can plot the graph. So this is how you do a decision tree classification model algorithm. So now let's look into this use case. Just a moment. Okay. Give me a minute, guys. There's some error. Okay. So now the use case we'll be looking into today is machine learning goes wild. Okay. This is about using data from captive animals your animals is referred to as individuals to infer wildlife behavior. We have seen an article yesterday about animal behavior and how animal behavior can be studied through all the machine learning algorithms such as k-means and knn, etc. So here what the researchers have done is they have remotely means controlled environment remotely tracked distinct behaviors of animals using accelerated data and machine learning, okay, which has been carried out successfully in several species in captive settings. Here, captive settings is nothing but a very big enclosure, or you can tell kind of a sanctuary, where these wild animals are bought and left, and they are given a certain year tag number, which includes all their details. For example, body temperature, body mass, and then his basic information like age, sex, etc., etc. Any diseases, contact, etc. Where they came from, location, etc. So, in order to study the ecology of animals in natural habitats, such behavior classification models need to be transferred to wild individuals. But the developments of these models usually require direct observation of the target animals. Target animals is what animal they are studying about. The main goal of this research of this remote tracking of captive individuals was to study and infer the behavior of wild, free roaming animals from acceleration data by training behavior classification models on captive individuals. Without the necessity to observe their wild conspecifics, they further developed models to validate the credibility of resulting behavior extrapolations. So, with the help of study of the data that they have collected, researchers are trying to predict future changes and behaviors of these animals that are in captive. They investigated 4 strategies to validate their classification outputs. So, and their approach is a or was a substantial improvement over the methods previously proposed in the literature or in the previous papers, as it generated possible results for wild behaviors of animals. They were successful in inferring the behaviors of wild animals that have been observed in the wild and to further illustrate their results. So they compared their results and the wild to see if the results they predicted matched the predictions they have made with the or from the animals in the wild. So they were successful. They used some of the technology such as animal-born sensors. These are used for temperature log, salinity logger, or microphones. Were used to study wide variety of parameters in wild animal without disturbance by human observers. So these animal-borne sensors made it possible to track the location of wild animals. The first attempt they made to remotely track animal locations was in 1960s through a VHF telemetry. So this was during 1960s, but recent years it has become common practice to track animal location with, as you all know, satellite systems. So this gave a chance for researchers to study where individuals dwell, or each group of particular individuals dwell. However, the spectrum of ecological questions that can be addressed by using location data alone is very limited. By combining such data with behavioral data, more in-depth studies of species will become possible. The main principle that's underlying remote tracking of behavior is to attach accelerometers to animals to record their body movements. The first major study utilizing acceleration data to study the behavior of animal was conducted in 1996. Since then, many studies have shown that acceleration data can be used to infer the behavior of animals by employing various machine learning algorithms. Extrapolation behaviors from acceleration data of wild individual is a challenge since it is often impossible to test whether the extrapolation behaviors are correct or not. Some models are trained and validated on same wild animals repeatedly, which requires direct observations of the stud individuals, at least for a certain period of time. So, the promising advance of behavior classification through machine learning is the ability to study the behavior of wild animals without observing them. So, using this technology, they have made it possible to study the behavior of wild animals without observing them and possibly by not disturbing them. There are some of the additional sensors they researchers have come up with are GPS or depth and speed sensors of for aquatic species, that is marine species, were employed to identify the behavioral executed in the animals. So in these cases, the information from the additional sensors was used to investigate the behavioral context the animal was in at the time of data recording, in order to delimit likely behaviors for studies in which no validation was possible. Various behaviors were grouped into broad, easy, distinguishable categories to reduce confusion of similar behaviors. So, this accurately inferring distinct behaviors of wild animals still poses a problem. So, that is how researchers have made use of sensors to identify the behaviors and differentiate them from one behavior to another. The main common behavior all the animals have is being wild. So, how do researchers differentiate that? So, that is why, till date, the researchers still poses a problem regarding that. So, how was this data collected exactly? So, after getting all the permissions and everything from the government officials for their study, researchers deployed UHF GPS collars, that is 1C light, 1C heavy, EOBS, Munich, Germany, and these are some kinds of built in systems that track the movements or all their behaviors of the animals. So, here, what the researchers have made is they have given these scholars to the animals who are in captive and some of the animals which are in wild. So both captive and wild individuals were tagged with the same type of sensors and acceleration data logging systems. So captive individuals were observed to train and test the models, and wild individuals were used to apply them. So that is how they have divided their, we can say in particular terms, data. For the training data set, 2 individuals were collected from an enclosure. So their enclosure mainly consisted of a sandy and stony substrate and was practically covered with concrete, grass, and weed. So there were many factors that they took into consideration when they had to select the animals. First was they were not afraid or they were lacking fear towards visitors and noises. Basically, you can say that they were not disturbed even when they are disturbed. And resulting possibility is to be observed outside their den for several hours per day. So the acceleration loggers that were embedded in their collars were set up to measure accelerations in short intervals of a frequency of 2 minutes. Data was recorded as 3 axes perpendicular to each other. There were 110 acceleration measurements taken for each axis in each measurement interval, resulting from the sampling rate and the number of measurements of each axis. The duration of each recording interval was 3.3 seconds. So in that 3.3 second, the researchers were able to capture data regarding or about the animal. So with that, they prepared or the inputs taken from them were feeding, grooming, resting, cacking. Okay, we might have a doubt what is cacking here. Nothing but they kill their food, they get food, they bury it to consume it later. So that is called as cacking. And crawling and walking. So data preparation. Here, the researchers calculated the summary statistics from raw acceleration data separately for each burst. Here, burst is nothing but the 3.3 window where they collected the data. That is called as a burst. So, to serve as predictors for the machine learning algorithm, the following predictors were calculated per axis. That is nothing but the business moments: mean, standard deviation, variation, coefficient of variation, variance range, kurtosis, skewness, etc. Okay, first order business moments, second order business, third, fourth business moments. So there were also additional predictors represent combinations of all three axes and were calculated according to the corresponding references. So in addition to summary statistics, they added a whole spectrum of fast Fourier transformation of each axis to the set of predictors. So the sum of functions in the axial rate was used to summary statistics and fast Fourier transformation calculations. So that is how they prepared their data. So this is how the researchers have used machine learning with airborne sensors and temperature loggers and salinity logger microphones to track the data about the wild captive individuals and compare them with compare the data alongside. So now we will start off with our next algorithm, that is simple linear regression. So the agenda for simple linear regression would be first getting to know what regression analysis is, and then a linear model, correlation analysis, ordinary least square, simple linear regression, error function, and advantages and disadvantages finally. Regression analysis. So why is regression used? Regression is used to study the relationship between two variables. We can use simple regression if both the dependent variable and the independent variable are numeric. Only when it is numeric, we can use regression. If the dependent variable is numeric, but the independent variable is categorical, it is not feasible to use numeric or regression. It is best to use ANOVA. Regression is used to study the relationship between two variables, but for those two variables, simple, if both dependent variable and independent variable are numeric, we use simple regression. If the dependent variable is numeric, but the independent variable is categorical, it is best to use ANOVA. So these are some of the situations where we can use regression. Just a moment. Okay. So the following are some of the situations where we use regression to test if IQ affects income. IQ is an independent variable and income is the dependent variable. How? If your IQ is more, you earn more. Or if your IQ is less, you earn less. That's a basic logic. So that is why they have given the income you get depends on your IQ. Testing if IQ affects income. So next is testing if hours of work affects hours of sleep. So hours of sleep is dependent, hours of work is independent. The more you work, or do you extend your work time, the sleep period reduces. So the time or we can say the period of work, sleep is dependent on the period of time, or you can say the hours of work you put in. So testing if the number of cigarettes smoked affects blood pressure. So number of cigarettes is an independent variable and blood pressure is the dependent variable. It is important to perform a scatter plot because it helps us to see if the relationship is linear. So we have two of the plots here. The first plot, when both the dependent variable and independent variable are numerical, we can represent data in the form of a scatter plot. In this example, the relationship between body fat percent and the chance of heart failure is not linear, and hence it is not sensible to use linear regression. Here, they have taken the example of the IQ and the income. If you have 60, your 60 IQ as 60, and your income as 40,000, 60,000, and 80,000. So here it depends. If your IQ is 60, you will earn in a range of 40,000. But if your IQ is 90, you will have a salary in range of 60,000. And if your IQ is 120, you'll have a salary in range of 80,000. So that is how you use a scatter plot to show the data. So next is the scatter diagram provides or plots provides a graphical representation to show or represent two continuous variables. We must be careful that correlation does not guarantee causation. So we have strong positive correlation, which is in a straight line and moving upwards. And you can tell this is a strong positive correlation. The graph that shows the IQ and income is a strong positive correlation. And moderate positive correlation is you have some scattered points of the data, but still it is moving in an upward direction. And then you have no correlation where the data is scattered. You have moderate negative correlation. The graph is moving downwards. And strong negative correlation is an opposite of strong positive correlation. And curvy linear relationship is when you have a curve to your data. So here, strength of relation by width or tightness of scatter. So we can judge the strength of a relation by its width and tightness of scatter. And it also determines strength of relationship. Example, if X increases, if X increases and Y decreases, it is negative correlation. Similarly, if X increases and Y also increases, it is called positive correlation. Here, if X increases and Y decreases, it is called negative correlation. And if X increases and Y also increases, then it is called positive correlation. So next is linear model. In regression, the relationship between y and x is modeled in the following form. Y is equal to a plus b into x plus e. So here y is a dependent variable, x is the independent variable, so they have taken the example of IQ and income, and they're telling here that y is a dependent variable, that is income, and x is the independent variable, which is the IQ. And a is the intercept, b is a coefficient, and e is an error term for each observation. So here the errors E are normally distributed. How can you test this? Is by plotting a histogram of a residuals of the regression and checking that they all have a bell shape. So correlation analysis measures the degree of linear relationship between two variables. Okay. Range of correlation coefficient -1 to +1. Here +1 is a perfect positive correlation and -1 is a perfect negative correlation. And if it is 0, then it has no linear correlation at all. As you can see here, R is equal to 0.4, just positively correlation. R is equal to 0, there's no correlation. And R minus 0.4, it is negatively correlated. Now, for this, we have a simple formula which is very simple to understand. N summation xy minus summation x summation y divided by root of n summation x square minus summation x whole square, n summation y square minus summation y whole square. So this mathematically how it is done. I will take an example of x, y, xy, okay. I will take some random data points here. Okay. 4, 3, 1, 2, 5. Okay. I have 5. So this is the n sample. N is equal to 5. Now y, and then here to calculate x and y, I have 4, 9, 2, 10, 20. So the total of this would be so next is x square. The square of x. And then we have y square. So the values which you get here are given to this formula. So the final answer, whatever, this is summation x, summation y, summation x square, and summation y square. So after getting all these values, the R, if you get a negative value, a positive value, or if you get R is equal to 0, these three apply. If you get a negative value, it is negative correlation. If you get a positive R value, it is positive correlation. And if you get R is equal to 0, then it is no correlation. This is about the correlation analysis. Next, we have ordinary least square. So ordinary least square regression is a common technique for estimating coefficients of linear regression equation, which describe the relationship between one or more independent quantitative variables and a dependent variable. So what is OLS? It is a common technique for estimating coefficients of linear regression equation, which describe the relationship between one or more independent quantitative variables and a dependent variable. So we can see fitting a straight line by least square is you do this formula. Y cap is equal to beta naught cap plus beta x cap. And the straight line here is y is equal to b naught plus b1x. And x naught is a specific value of x, the independent variable. So these are the data points. So this value is a mean value of y where x equals x naught. We already saw what x naught is. So perpendicular to that is an observed value of x when x equals x naught. And the distance between that point and the point on the straight line is the error term. So this is about the ordinary least square. Now is the simple linear regression. We have r squared, which is also known as coefficient of determination. Represents the percent variation in output. That is nothing but a dependent variable. It's explained by input variables or percentage of response variable variation that is explained by its relationship with one or more predictor variables. So here there's some conditions for R. Higher the R square, the better the model fits your data. And R square is always between 0 to 100%. R squared is between 0.65 and 0.8 when we have moderate correlation. And we have R squared greater than 0.8 when we have very strong correlations. And mathematically, we represent as y cap minus y bar whole square as measure of explained variation, y minus y cap whole square as measure of an unexplained variation, SSR plus SSE, SSR plus SSE, which is nothing but summation of y minus y bar the whole square, measure of total variation in y. So R square is nothing but SSR by SST. Your SST is nothing but SSR plus SSE. So which has to be in range of 0 less than or equal to R square less than or equal to 1. So next we have simple linear regression. We have some of the topics where we call them as prediction and confidence interval, prediction interval, confidence interval. So these two are types of confidence intervals used for prediction and regression and other linear models. So let's look into what they are. Prediction interval represents a range that a single new observation is likely to fall given specified settings of the predictors. So confidence interval of the prediction, it represents a range that the mean response is likely to fall given specified settings of the predictors. So the prediction interval is always wider than the corresponding confidence interval because of the added uncertainty involved in predicting a single response versus a mean response. So if you have y as continuous data and x as single and continuous data, then you directly go to simple linear regression. However, if y is continuous and x is single and discrete, then you create a dummy variable. And then after creating a dummy variable, you go to simple linear regression. We have something called as error variable, which are required conditions. So error E is a critical part of the regression model. So we have 4 requirements involving the distribution of E, which has to be satisfied. So the probability distribution of E is normal, and the mean of E is 0. The standard deviation of E is SE for all values of X. The set of errors associated with different values of Y, the set of errors which are associated with different values of Y are all independent. Okay, so now if we come into advantages of simple linear regression, we have the algorithm is very simple to implement and easier to interpret the output coefficients. When you want the relationship between both the dependent and independent variable, which has a linear relationship, this algorithm is the best to use because of its complexity, which is much lesser compared to other algorithms. And linear regression is susceptible to overfitting, but it can be avoided using some dimensionality reduction techniques, regularization, that is L1 and L2 techniques, and cross-validation. So next is the disadvantages. As we saw here, it is a simple to implement and easier to interpret, but by any chance, if we have outliers, it will have a huge effects on the regression and boundaries that are linear in this technique. Outliers will have a very great effects on the regression line and its boundaries. So diversely, linear regression assumes a linear relationship between dependent and independent variables. So the mean, it assumes that there is a straight line relationship between them. It assumes independence between attributes. But then linear regression also looks at a relationship between the mean and the dependent variable and the independent variables. Just as a mean is not a completely descriptive of single variable, linear regression is not completely descriptive of relationships among variables. So these are the advantages and disadvantages of simple linear regression. So this completes the simple linear regression. Now let's look into the code. So here we are importing the libraries that are useful to us, that is pandas and numpy. We are reading the data set, that is the data set contains risk position and risk score. This is about a animal to human spillover, meaning the diseases that gets or contagious, or we get these diseases from wild animal to humans. So what is the risk score of animal to human spillover? These are the risk rating scores. Is the risk position of that particular disease or virus or whatever it is, and its score, where it stands. So first, we describe the data. So we get the count, mean, standard deviation, minimum, maximum. And then we visualize the data. So we can see here the risk score is between 0 to 100 and somewhere after 400, meaning this is not that risky, but the 0 to 100 risk score of the pathogens is troublesome. This is the box plot of the data. The histogram of the risk position. And the box plot of the risk position. Scatter plot, which is a bivariate graphical representation, shows us the graph of two variables. So this is how the graph is distributed. We have all the data accumulated from between 0 to 100. So this is the correlation of the data. Okay. So first, we input the model and we fit the model and we call the model summary. And then we predict the risk position of the data. And then we try to draw a regression line. We also find out error calculation. And we build model building on transformed data. We build the model on a transformed data. So we did the log transformations, x is equal to log waste, y is equal to at. So here, scatter, x is equal to np.log spillover, and y is spillover for risk score. We are giving it as a color brown. And we are doing the correlation coefficient with np.log of spillover risk position and y as risk score. So this is a model 2. We keep on fitting the model until we get the best scatter or the best model. Okay, and then we split the model. So train and test. Is a final. We fit the data or the model and get the final predictions. We get the prediction on test data and prediction on train data and model evaluation on test data as well as a model evaluation on train data. So that is how you fit your simple linear regression model for any data which has dependent and independent variable. So This is your simple linear regression. So the use case we'll be taking now is about the data we have read. Ranking the risk of animal to human spillover for newly discovered viruses. So the significance of this study was to get to know about the recent emergence and spread of zoonotic viruses, including Ebola viruses and severe acute respiratory syndrome, that is nothing but coronavirus 2. It demonstrates that animal sourced viruses are a very real threat to global public health. Virus discovery efforts have detected hundreds of new animal viruses with unknown zoonotic risk. So they developed an open source risk assessment system to systematically evaluate novel wildlife origin viruses in terms of their zoonotic spillover and spread potential. Spread potential is how far the disease can be spread and how many casualties will be there. So their tool will help scientists and government to assess and communicate risk information, informing national disease prioritization, prevention, and control actions. So the resulting watch list of potential pathogens will identify targets for new virus countermeasures initiatives. So the system that they have built, it captures all these are just two examples of viruses, but there are many viruses, mostly 100 to 200 or many more plus viruses, where they take into account of all of these symptoms, viruses, their structure, etc. And they store it in a database. And whenever a new virus comes in, they go into a cycle of getting, suggesting or comparing all of these viruses and checking if they have a match that is similar to the new virus that is come up. So that way they can have or do risk assessments, prevention methods, and can take control actions towards this new virus. So whenever we encounter a mass or a virus like Ebola virus and coronavirus, we had a death toll and economic loss resulting from a severe acute respiratory, yes, from this virus. Pandemics are stark reminders that we are vulnerable to zoonotic virus threats. So, strategies are needed to identify and categorize beside being or following safety measures. Strategies are also needed to identify and categorize animal viruses that pose the greatest risk of spillover and spreading humans, and also inform public health interventions. So they used an expert opinion and scientific evidence to identify host, viral, environmental risk factors contributing to zoonotic viruses spillover and spreading humans. They developed a risk ranking framework and interactive web tool that estimates the risk score for wildlife origin viruses, creating a comparative risk assessment of viruses with uncharacterized zoonotic spillover potential alongside those already known to be zoonotic. So the samples they collected were 509 and 721 samples from 74 635 animals as part of a virus discovery project and public records of viruses detection around the world. So they ranked the spillover potential of 887 wildlife viruses, validating the risk assessment. The top 12 viruses were known as zoonotic viruses, including this 12 includes COVID. So, several newly detected wildlife viruses ranked higher than known zoonotic viruses. So, using a scientifically informed process, they capitalized on the recent wealth of virus discovery data to systematically identify and prioritize targets for investigation. The publicly accessible spillover platform can be used by policymakers and health scientist to inform research and public health interventions for prevention and rapid control of disease outbreaks. So, this data that they have collected, this 509,721 samples from 74,635 animals, they have named the data was pushed into a database, and this database was called as spillover. So this database, which is made publicly available or accessible, was used by policymakers and health scientists to inform research and public health interventions for prevention and rapid control outbreaks. So here, this spillover is a living, interactive database that can be refined over time. Meaning, if any new data or any new virus is again identified, this can be sent into the database. So, refined over time to continue to improve the quality and public availability of information on virus threats to human health. So we now live in an era in which threats posed by viral pandemics are a daily reality. A single lethal virus can emerge suddenly and spread rapidly to every household and every community without regard to national borders or to social and economic standing, which is very true. Recognizing the importance of emerging infectious diseases, the World Health Organization highlighted disease X, which is a currently unknown pathogen capable of causing a serious human epidemic, as a target for research and development. However, despite increased investment in pandemic prevention and knowledge gained from previous outbreaks, such as coronavirus and Ebola virus and Zika virus, we are still unprepared for the severity of the viruses that may come up. So the basic global economic loss during coronavirus was approximately 28 trillion. So SARS is one of many potential viral threats to humans. There are just over 250 known zoonotic viruses that have previously spilled over from animals to humans and caused diseases in people. So while these viruses are ongoing concern to human health, as repeated Ebola epidemics demonstrate, they are yet to identify viruses pose an equal, if not more serious threat to humanity. Approximately, we have 1.6 million undescribed viruses that exist in mammals and birds. Up to up half of which are estimated to have the potential to spill over into humans. So, discovery efforts have initiated the process of investigating potential viral threats. So, these researchers sampled wildlife at high risk human disease transmissions interfaces in over 30 countries, resulting in the discovery of hundreds of previously undetected viruses. Although interesting, virus discoveries creates a plethora of data without direction on where to focus efforts to prevent viral spillover that could lead to future epidemics and pandemics. So, for this, a strategy is needed to evaluate viruses and identify those that are most important for further investigation and surveillance. So, the risk each virus possesses to human health is not equal. Two viruses may be nearly identical, one zoonotic and the other not. However, several factors about the virus, that is, host, the organism in which the virus can live and multiply, environment, the location, the ecology where the host lives, and related human behavior influences the likelihood that a virus will become zoonotic and spread within human populations. So, here the risk assessments, such as those used by lenders, account for variances among risk factors in order to determine a comparative risk score. So, previous studies and tools using this approach for viruses have been insightful, but very limited in scope by focusing on narrow groups of viruses or few risk factors. But They have come up with some of the risk ranking methods. Since zoonotic spillover risk inherency is characterized by the ability of an animal sourced viruses to infect human and cause disease, they looked for factors that covered topics relating to the likelihood of viruses transmissions from animal to human and the ability of the virus to cause disease and spread within human populations. So they identified a total of 50 potential risk factors, including all those that could be identified in the peer to peer reviewed methods, as well as that were identified through viral discovery fieldworks and surveys. So the data or the spillover, which is a database of viruses detections in wildlife, confirmed genetic sequencing and the necessary metadata to characterize the viruses according to the risk factors described. Most host species were limited to classes of mammalia, reptilia, and amphibia. So the database contains 35,751 rows of unique detections with metadata for 887 viruses from 19 virus families separately. So initially, virus detection data were collected from multiple sources, including viruses detections during our viral discovery project. So the National Center for Biotechnology Information also helped with the discovery of viruses to put them into their databases. So this data includes availability, virus taxonomy, and identifier, that is number, the host species, what is a virus takes it host species as, taxonomy, sample type in which the viruses are detected, and primary disease transmission interface, and longitude and latitude where the animal was sampled. And finally, and most importantly, the country of detection. So this was how the spillover of the viruses were ranked based on the risk that the humans possess. Thank you for your time. This is for today. We'll meet in the next session.